Welcome back. We have a test on Monday. I know it's old news, and that's the way I want it. I have a question for you guys, and it's inspired by the questions that I had last time on the test. When you guys are taking, when you guys sit down for one of my tests or maybe some other professor's tests, do you ever have the sense that you should just know the answer when you finish reading the problem? Do you ever feel like you need to know the answer? That's wrong. You'll never. I mean, and that's why. So several people nodded, and it is true that when you take a test in high school, in current high schools, I think, and in other disciplines, it's you feel like there's a true or false answer, or there's an answer, a short answer, or there's an answer that you should have in your memory banks. And no engineering test I've ever seen is really built around that. I mean, yeah, sure, there's sometimes we have weird questions, but most of our questions are problem-solving questions. And by definition, you should not know the answer, just from reading the question. For the easier problems, you should know the direction that you want to go. You should know how to get to the problem. You should know what terms you should multiply and what terms not. But for many other types of questions, you may not even know the route to take that will get you to the answer. And so I bring that up because you asked how people trip up. What should you know? And it dawned on me that when I read that sometimes people will I get the sense sometimes that maybe you think that the answers should be right there at your fingertips, and it's not. What I really look for is your thought process. What do you know to bring to bear to the problem? And are you working towards that? With your work. And so please don't be frustrated if you don't get there within a couple of lines. It may be or right away. So just have perseverance and just go back through it. And remember, if you don't know the answer, don't panic, because you're not supposed to know. Probably not supposed to know the answer, just from reading the question. And it's very different from real life, isn't it? Real life, I say, where's the nearest 7-Eleven? You're supposed to know that to answer my question, but it's equivalent, it's more like, well, I know how to look at a map, and I know how to Google it and find out where it is, and here's how you get there. So, but anyway, that's a bad analogy, but that's what I'm thinking of. Okay. All right. So, this is. This is the E3350 Communication Systems. This is Lecture 20. And this will pretty much take us through the end, I think, almost the end, if I hustle a little bit, which is not my intent, to get to towards the end of pulse code modulation. I'm Professor Duncan McFarlane. And this is April. What is the date today? The 9th? The 9th. And I think it's the 2014, but I can never be sure. I'm in the right century, right? So let me review the architecture for pulse code modulation on our transmitter side. Comprises 3 steps. The sampling, that's block A, if you want to think of it that way. And the key to that is that we want to if our signal has a bandwidth capital B, we want to sample at twice that frequency. Okay. Now, many signals don't go to 0 at a particular bandwidth B and then stay at 0 forever. Most of our signals trail off And there's always some little bit that may be higher than a certain cutoff frequency that we care about. And so when that happens, we as designers, manipulators of our signal, may elect to put a hard low-pass filter in front of our sampling step. We may say that we are interested only up to this bandwidth B, knowing that our user, who we really don't have any control over, our user may violate that condition. And if our user violates that condition, it might mess up significantly our processing of it. And so we may want to take proactive action to say, no, you won't. You bought this system, it's going to go up to capital B as a bandwidth. Any higher than that, that's going to cause trouble for us and maybe even other users. So what we're going to do is we're going to limit you to the use of the bandwidth that we specified. And so we may put in a hard stop filter there to say you won't go above capital B. Okay? And that's our right as a design engineer. And it's something that you may not obviously think of, but it's okay to do. It's okay to do that if you say, you can drive, you have your bandwidth up to capital B. There's no reason why you need to entertain them to go beyond that. There's no reason why you should allow them to go beyond that. Okay, especially if it makes sense from the architecture, from the economics of the system, and so on. Okay. So that's just something that's often done, and it's a good idea to do it because it'll guarantee that your sampling behaves correctly. Okay. As I pointed out last time, sampling takes us from a continuous time signal to a discrete time signal. Okay. So we segment things off, or we sample things off in the x-axis, the time axis. And then what we talked about last time was block B, or the quantization. And that's really taking the vertical voltages, lumping them into cells, into blocks, and saying everything inside this range of voltages. I think I used a range of delta, was going to be one digital code. Either a 3-bit code, a 4-bit code, an 8-bit code, 12-bit code, however many transistors I want to throw at the problem, however confident I am on taking a range of voltages and dividing down, right? Because remember, if I say that I have a microvolt of range, gosh, I've got to control all my voltages to a microvolt. And that may be easy or hard to do, depending on the temperature environment, whether I'm doing this in an integrated setting or soldering together discrete components. My goodness, that sounds difficult to do to achieve a microvolt if I'm working with lump circuits. Okay. So quantizing finishes the job of creating a digital signal. Okay. What we'll get to today. We'll finish up some comments on this A to D conversion, this quantization, and what we'll also get in today is the final step, which is encoding all these blocks together. A, B, and C give rise to the PCM transmitter, and then we're ready to send this down the channel, out over the airwaves, down a transmission line, a fiber optic cable, or what have you. All those examples are analog channels, not digital channels. So the signal that's produced out of here has to be, and I have to say this carefully, and you have to listen to this carefully, an analog representation of a 1 or an analog representation of a 0. Okay? So encoding takes us from a digital signal to an analog representation of a digital signal. So we start with a continuous time analog signal. We go to a discrete time analog signal. We go to a digital signal, and then we go back to an analog representation of a digital signal for sending down the channel. And the interesting thing about this encoding that we'll see is, depending on what channel we have, there's certain choices for the encoding scheme that makes sense or makes more sense than others. In other words, we can optimize encoding given the constraints of the channel. And money, of course. And the economics of the situation, of course. Okay? So that's the overview of the pulse code modulation. And then the receiver acts in reverse to decode and then reconstruct. And what we should have is M of t. Okay? But we know we've lost information in the sampling, for example, or the quantizing, for example. And so what I usually do, and I don't want this to be confusing, so I want to go over this. This is a point of notation. It's a small point of notation, but I want to be clear about it to you guys. I usually describe the message signal that comes out of the receiver as M prime of t. And what I'm saying with that is I'm not talking about derivatives or anything like that. I don't use that notation for derivatives. What I'm saying there is that this M prime of t, if everything was done absolutely perfectly, that would equal M of t. But it's not, because it's been processed through a faulty channel, a channel with impairments, a quantization that introduces an uncertainty of delta. Some people call that a noise. And then decoded and reconstructed by real elements. And so M prime of t is not equal to M of t. It's going to be close. It's going to be a reasonable representation of M of t, but it's not going to be exactly. And so it's easier for me just to say that this is close to M of t, but not exactly. And so I denote that closeness with a prime. Okay. Silly notation, but I don't want it to be confusing. Now, quantization. Let's see. A couple of points of review on that. One piece is the transfer function, V in to V out. So I have a stream of samples. Actually, I wrote it as a continuous time. I'm sorry, but it should be a stream of samples that come in, discrete time samples, and depending exactly what voltage you come in at, you get assigned a certain output voltage. Okay? So, for example, everything here between 0 and delta, to use the notation that I did last time, everything in this range here which is this whole part of the message signal, gets assigned one value of voltage, which ultimately leads to 1 point on my digital, notation. And you see that if you care about all this changes, you've lost them. Okay? You've lost that. You may not care, in which case you're fine, but I'm just saying that that's what this transfer function, the stepped transfer function, means. Okay? So depending on how you draw this picture, you have something that looks extremely distorted like that, or something that looks, smoothly represented. This is determined a large part by the number of levels. And so you'll have we'll use the notation m for the number of levels. If I have n bits, that's the number of spaces that I have. 3 bits, 4 bits. How many ones and zeros represent that single voltage? That's the number of bits. Then m is equal to 2 to the n. Okay. We did the example last time of 3 bits. 3 bits, so I had 2 to the 3. 2 times 2 times 2 is 8. So whatever voltage range I had, I divided that up into 8 bins. Okay, and I think I went from -8 to +8, 16 volts. So each bin was worth 2 volts. Okay, 2 volts of notation. Now, remember that I sample. I wait a sampling period T sub s, and then I get a new voltage. Okay? So I have the information from that sample voltage. I have to send down this pipeline. I have to send down all that information that describes that sample before the next one is ready. So I have a time, capital T sub s, to get all the bits out. I have a time, capital T sub s, to get all the bits that describe that sample out the door. I can't fall behind because in my communication system, I'm on all the time. I'm on all the time. So there's no buffer here. Every buffer will overflow. Okay? Lucy at the chocolate factory. I know you all went home and watched that video, I hope. I hope you can find it. I haven't looked for it. I know if I were a really cool professor, I'd pull it up and we'd watch it in class. But I'm not. I'm not a cool professor. So, all right. So we have a capital T sub s to get all those bits out. And so what we have is the bandwidth of the system must be the number of bits times capital 2B. I'm sorry, times 2 times capital B. So what I'm saying there is within a time T sub s, and T sub s by Nyquist is 1 over 2B, I have to get all n bits out there. So the speed or the bandwidth of my channel and my encoding and all my electronics has to be n times 2B. So if I add a bit, n, if I go from 3 bits to 4 bits, I exponentially grow 2 to the 3 versus 2 to the 4. 2 to the 3 versus 2 to the 4. I double the number of levels that I have. I double my precision. That delta halves, but I only scale linearly with the bandwidth. So that's a pretty good trade-off. I grow exponentially in the precision, but I linearly grow in the bandwidth. It's still a trade-off. It's still a trade-off, and it will catch up with me at some point. But at least it's a linear to an exponential, even though 2 is a fairly, well, I won't go there. Okay. There's another thing to consider. So this is 1, this is 2, this is 3. There's another point to consider. Now, there's a concept that you may have heard the words, and you probably have a good idea of what it is, but I want to kind of go through it because it's a really fundamental and nice concept. And that's called the dynamic range. Okay? And the dynamic range has a lot to do with the number of levels that we're talking about. In fact, the dynamic range is usually expressed in dB, and it's usually the log base 10 of m, the number of levels. And just to turn this into dB, I have to make a choice here. If I'm working with voltages, then that's got to be 20 log of m, and that gives you dBs. Okay, that gives you dBs. Now let's explore a little bit more about what I mean by dynamic range. And the example that I like to use is 2 types of thermometers. Okay? So if I have a thermometer that I buy at like CVS, and I want to measure my temperature. Okay? So let me make some notes on this. 2 thermometers, dynamic range. Okay? The first one is temperature of person. Give me some specs or some requirements on what we might face if we wanted to take the temperature of a person, one of those digital thermometers that we put under our tongue, and it beeps after a few seconds, and we take a look at it. What are some of the requirements, or what are some of the specs for that temperature range? Okay, so it should be in the range of 98.6 because that's allegedly a healthy person. Okay, how do we use that information? The simple output is a display of your temperature. So how do I know that? So over 100 is something that I care about. So do I want to be? Does it have to be sensitive to more than 100?
Yeah.
Okay.
Quantize it a certain way to make it.
So let's hang on with that. Quantize it is going to be important, but let's look at the specs. What's the range that I want it to work over?
90 to like 106, 107.
So one range to work over is somewhere like 90 to, what did you say? 109. I'm going to make my life easy. 110, and I think that's a delta T of 20. Okay, a delta T of 20. Now, why did you pick 110? You said I was really interested in over 100. Why did you now come back and say, cut it off at 110? I don't care about somebody who has a temperature of 111. They're probably dead at that point.
105 or higher, causing brain damage.
So things get really bad if I'm north of 110. And probably upon review, if I wanted to save some money on electronics, I might dump that down to 108. Or even if I do my design right, I can say if I'm at 105 or 106, I can have a hugely loud beep saying that basically says get to the hospital immediately, or jump in an ice flow or something like that to get your body temperature down. So you're absolutely right. There's a limit. There's a limit to how high you need to measure. It's also very rare that you're going to get to 110, as you pointed out, because if you're at 106, you're going to die, and then you're going to start to cool off. 108, I guess you're going to die. Okay? So again, and I hate to be morbid about this, and I'm not trying to be morbid about this. I'm certainly not trying to be funny about this. But what I'm trying to do is this is a serious requirements discussion where we draw a line and say we don't need to go beyond this point because of this reason. And this reason, yes, it happens to be life and death. Okay? Now, to ameliorate this a little bit, the cheap little thermometers that you get at CVS are, there's going to be all kinds of other compromises based on the economics. But it's the same argument if you're doing it in a doctor's office. What about the low end, 90? Why'd you pick 90?
I feel like 90 is too low. That at that point you're in hypothermia. So
You're also
it up to 8 to 95.
You're also in a world of hurt if you're at 90. And so maybe you could revise this if you wanted to save some money. So the 95 was suggested. That sounds a little bit close to 98.6 just because of uncertainty. And temperature is actually a pretty hard measurement to make. Temperature it's easy to be precise. It's really hard to be accurate on temperature. I mean, just think about the art of measuring temperature. If you measure it in your mouth versus under your arm, you're cooler under the arm than in the mouth, and that has nothing to do with what's going on inside your brain temperature or what's going on inside your chest cavity, where important tissues are being affected. There's going to be a heat gradient. So you're going to measure a very, very precise temperature in your mouth and make a decision on that, and that's nothing, and that's probably another couple degrees away from what's going on inside your head or right next to where the virus is really attacking and really doing all those exothermic reactions that are pumping things out. Okay? So yeah, so delta T. So maybe we can quibble even more and go somewhere between 94 and 106. I'm not going to quibble with you on either of those. Okay? Instead, I'm going to ask the level of precision. You still can't read that, but it's almost legible. Precision. How precisely do I need to know my temperature? If I get 98.6 versus 98.8 versus 97.8, 98.2, what's the level of precision that I want to make a decision based on? Within the tens place. So I need to know the difference between 98.6 versus 98.7. So that's the tens place. So I need to know to within 0.1 degree Fahrenheit. That's the assertion. Discussion. You're buying a thermometer. One thermometer is $8. One thermometer is $20, and it has 0.1 Fahrenheit precision. Another thermometer is $8, and it's 0.4 or 0.2. What's your price sensitivity versus temperature? I have also a dollar thermometer, and it gets you to 5 degrees. The difference between 98 and 103, you don't know. Which one of those? How many of you would buy the $1 thermometer with a 5 degree precision? I'm not seeing any hands. I'm going to paint it. I'm going to have the plastic housing be a really, really nice pink. No? Green? No. All right. Well, what about the $20 0.1 degree precision.
These are 0.4.
I've got one person who cares about that. I've got two people. I've got two people. What about 0.2? What about 0.2 for $10? Now a lot more people are doing it, and that kind of market survey and that kind of thinking is actually a reasonable way to do it. I mean, a lot of you, some of you are in senior design or will be soon, and that's exactly the kind of common sense thinking, And notice one thing: when one person thinks about an answer, they get close, and they guide the rest of the rest of the group in their thinking. Okay, so what happens a lot of times is once you bounce this around, if one person does these requirements in isolation, they're going to get them wrong. But if several reasonable people get together and they think broadly about the problem, they'll get much better. And then if you do a full market survey over all kinds of people, who face a lot of different, illness problems, you'll get a better range. But I think what we boiled into is, and that's not a temperature joke, we have something about 12 to 14 degrees, and we want to measure it to what? What did I say? 0.2? So that's 5. So am I doing 5 times 12? And that's 60 readings. And 60 readings is close to 64, which is a power of 2. So what is that? That's 2 to the what power? 2 to the 3 is 8. 2 to the 3 is 8. 8 times 8, so that's 6, right? That's 2 to the 6th power equals 64 m. 2 to the n equals m. 2 to the 6th equals 64. Did I do that right? Did I do that right? Yeah. Okay. So that's one kind of thermometer. And what I can say is my dynamic range is related exactly to these number of levels. 64 is a linear measure of my dynamic range. When I do m, when I do the log of m, I get that in dBs. Okay. So if somebody wants to do the log of 64, that's log of 100 is 2. 64 is less than 2, 1 point something. Multiplied by 20, 1.5 times 20 is 30, somewhere in that range. I'm checking my cheat sheet and it's 36. Okay? Logs are fun, especially base 10s. That's why we like dBs. Okay? All right, now temperature of the patio outside or the porch outside your apartment or outside your house. In Texas. But let's face it, you're going to sell this thermometer. You're going to sell this thermometer all over the world. But the habitable world, right? So think Texas. What's your range? What range am I interested in?
All year.
I don't know. The question was all year. Am I going to sell 4 thermometers? One for winter, one for spring, one for summer, one for fall? I guess it would only be 3 because spring and fall are the same. So are you going to ask your customer to go out and it's spring, it's daylight savings time. I'm going out and change my thermometers. I don't want to be sarcastic, but again, this is all common sense. So 4 thermometers or 1? 1 thermometer. Even though I can tell, I'll buy a good thermometer and it'll be 4 times the expensive. As expensive as, okay. So yeah, range for the entire year. Minus 20 degrees Fahrenheit is the low. What? 120. To about 120 Fahrenheit is the high. Anybody want to cheat on that or change that?
Is that our setting temperature or is it the temperature on the patio or outside?
Well, I'm okay. That's a good question. I imagine that I'm outside, I'm inside, and I have cold, refreshing beverage in my hand, or I have a hot cup of coffee in my hand, and I'm making a decision whether or not I want to go out on my porch or my patio to sit down and enjoy that. Okay. Maybe I'm also deciding whether or not to put on a sweater or to change into shorts to go outside. Okay. These are life things. Okay. So minus 20 to 120 degrees Fahrenheit.
Is this for Texas or for the world or for the U.S.?
Talk to me. Is it for Texas or for the world or for what would it be in Texas?
Be somewhere around maybe 10 to 120.
Texas, 10 to 120. What about Minnesota? Or Canada? Minus 40. Minus 40, and yeah. To 100. I've seen 100-degree heat in Alberta. It's not fun, but I've seen it. So that's 110, and that's about 140 of a range. So again, my and that's about 140. So my range, and take a look at that number. That's about 140 degrees, 120 to 140 degrees. Now, what about the precision? What about the precision that we need? How precisely do I need to know the temperature? Does anyone know? Okay, 2 degrees Fahrenheit is one answer that was shouted out.
I'd be willing to go for 4 or 5.
4 to 5 degrees Fahrenheit.
I'm not that sensitive.
Who else?
Like 1 or 2.
1 degree Fahrenheit. It's actually kind of interesting because Fahrenheit's a neat scale, and how many of you live in an air conditioned apartment or central heating apartment? Do you have access to the temperature in there? Is it a little digital display? So what I want you to do is I want you to experiment a little bit. See if you can tell the difference between 1 degree, 71 and 70. Okay, and I bet you can. I bet that's about the limit that what you can measure, though. Okay, so you might, and remember, if it's an outdoor thermometer, 2 degrees is probably right. So let's see. Every 2 degrees, so in a factor of 10, that's 5. And just to line up with my other calculations, because I cheat a little bit on this. I get the same number of 60, which means the same 6, 2 to the 6th power. So two different applications of a thermometer, one for inside your body and the other for outside your house, leads to exactly the same dynamic range. Okay? And I use the word exactly as a dramatic, because we have some wiggle room in all the numbers. Okay? But we're not far off. And it actually turns out that a very popular A to D is 8 bits. Why, 6 is a funny number. 8 is a nice number. So in both of these instances, I can buy a dirt cheap A to D converter that's 8 bits and do better than our common sense spec on both of those. Okay. So what am I doing about this dynamic range? Well, my dynamic range is actually some measure of my signal the number of degrees Fahrenheit divided by my uncertainty in my signal. And that uncertainty in my signal I've labeled as delta for A to D. But when we were looking at our specs, they were just the uncertainty in how I measure it. So this dynamic range, which in a digital study we talk about the number of levels, 20 times the log of the levels, is also 20 times the log of the signal in voltage divided by the noise in voltage. If your signal's in power and your noise is in power, then that becomes 10 dB. Okay? So this issue of dynamic range is a very, very important fundamental engineering concept. And so what we do, is, of course, to present it is we hide it under this discussion of analog to digital conversion. But it transcends so much more than that. Okay? So this one, from a decision-making perspective, is very, very important. And it's nice that it's related directly to the number of levels that we're quantizing with. Okay. By the way, if my noise in measuring the temperature is much less than my delta, then this holds fully. If my noise in measuring my temperature is much greater than my delta, then it doesn't matter if my delta is 0.1 volts, if my noise is 0.5 volts, because I'll just be measuring the difference between noise. It's random. So that's one of the problems with noise is you consider the worst case noise, not. So of all the noise sources that you can have, you consider the worst case. And so generally speaking, what you do is you drive your delta, this delta here, down to about the level of noise that you expect. And that's where you sample. Okay? So again, number of levels, the connection to the signal to noise, that's a nice connection to know. Okay? Let me give you a chart of these guys. I think this will all work. Yeah. Okay. So this is off my website. I have a set of slides called PCM charts, and this is a table. I think I started to do a table last time that is kind of crummy. This is a more detailed table. It's typed and everything. You can see. Play with my toy here. You can see here's my number of bits, n, and 2 to the n there. So we were sort of looking at 6 bits to give us 64. I told you there's a really nice there's a nice cheap A to D at 8 bits, and that gives you 256 levels. Something like a temperature measurement, that's pretty darn good over those ranges. Okay. The bandwidth is just the multiplication of 2 NB, and so this is just normalized in terms of B, so you can just see the linear increase as you go up in that. And all this number does is take the log of M and multiply it by 20, and so you see that every time you double, it's 6 dB. 6 dB is a doubling in voltage ratio. 3 dB is a doubling in power ratio. 20 dB is an order of magnitude in voltage. 10 dB per decade is a power number. Okay? Just got to be a little careful about that. Okay, 12 bits is a typical instrumentation amplifier more or less today. Okay? And in 12 bits you get 4,000. You get 4,000 levels. Okay? So that gives you 3 decimal places. 4,000 and a little bit better than 3 decimal places. 70 dB of dynamic range. That's pretty good. That's a pretty good instrumentation amplifier. Pretty good instrumentation spec. Okay, sorry. Yeah. That's where a lot of this is where you're doing, if you're doing cheap electronics, consumer stuff, you're going to be sitting around here. It's good enough. Pretty easy to design with. If you're doing a senior design project, you'll have no problem laying out a board with an 8-bit A to D. You won't have to worry too much about the temperature of that. That'll be. If you want to be a little bit more ambitious, you do a little bit more careful design, more precision resistors and so on. You'll get to 12 bits. There's plenty of applications that are down in this range, even below 16. And it's not that that's unfeasible. It's just that it gets very expensive on the actual A to D. And it also gets extremely difficult to work with. Look at just the difference between 4,000 and 65,000 levels. The other way to think about that, the way I think about that is, do you remember that staircase of the transfer function? That's the number of steps on the staircase. And the number of steps you have on the staircase are the number of voltage references that you have to have on your A to D chip. If you establish those voltages, say, on a resistor chain, that's the number of resistors that you have to keep controlled on that chain. Or the number of voltage references that you need to have on chip. That gets really unwieldy and really difficult to keep them there. So it's one thing to design that voltage, that resistor chain. It's another thing to actually implement it. And I'm taking some license by talking about a resistance chain, because it's usually set drops of a junction. Okay? Which is controlled a little bit better, but still you have to control the temperature of that. So what I'm getting at is it's one thing to wave your hand and say, I want 96 dB of dynamic range. It's another thing to say, okay, that means controlling 65,000 voltage levels to get that. The other thing that happens is other noise sources come into play. And one of the lectures that I probably will get to is shot noise, which is sort of the fundamental quantum noise. I don't know if I'll have time this semester, but I often try to talk also about thermal noise, Johnson noise. Johnson with an H, not two S's. Okay, so I try to talk about that as well. I don't think I'll be able to get to those lectures this semester. But what will happen is your delta will now be confused or impaired by those noise sources. And so even if you specify a 16-bit, or what happens a lot of times is the spec sheet will read a 14-bit A to D. It'll read a 14-bit A to D, but by the time you look at any sensible application, you're down to 12-bit A to D in an instrument. So that's an example of specifying the design instead of the application. Specsmanship. Those darn product managers. Yes, sir.
I mean, it's quite hard going from HD, but how about D digital to audio? Because I know for like headphone DACs, like there's commonly 16-bit or 24-bit.
So this is A to D quantization, and the D to A is a lot easier.
Okay.
That doesn't require the voltage levels as much. It doesn't require the.
This would be for like microphones, I'm guessing.
Yeah, a 12-bit. That would be pretty good sampling of your, the number of levels that you hear. I'd be surprised. I don't know the psychophysics of that. I'm hesitating to say, but I would guess that 4,000 levels of volume is pretty good. But again, it depends on how small a whisper you need to hear versus how large a shout you need to hear. And you may care about one range versus another range separately on separate occasions. That's the other thing I wanted to talk about. Let me go back to my thermometer. Glad you mentioned that. Let's go back to my thermometer. If I want to make a difference, if I want to measure a difference, I also need to worry about dynamic range. In other words, if I want to know on this temperature, if I want to know a 0.1 difference at 100 degrees, and I also want to know a 0.1 difference at 10 degrees, I have to make a precise measurement at 100 degrees and use the same reference point to make that precise measurement at 10 degrees so that I can difference those two readings. Okay? So I can't use a thermometer that I design here and a thermometer that I design around 10 degrees and difference those two, because those are two completely different reference scales. So I won't get that difference reading. So if I'm trying to make a measurement of a small number, a very precise difference between two very, very different voltages, I'm stuck with a dynamic range problem. Okay? And that comes up a lot in communications. I want to know a small variation on my signal. I want to know a small variation on my noise. It means I have to somehow I have to relate those two measurements together, and that's a challenge. Okay? Okay. All right. So we digressed a lot on dynamic range, but it's a really important concept, and that's why I wanted to kind of go over that with you. I have a feeling that for many of you, when you start having fun with your senior design project, you'll run into that. If you use an A to D or you use some sort of measurement, you're ultimately going to have to think about that. Okay. Now, I'm going to very briefly go through three types of noise issues, impairments with A to D. Okay? The one thing, if I have a waveform and I decide that I'm only interested up to this range, then I'll clip. And as soon as I clip, I have a sharp slope discontinuity, and the only way to pull that in with a Fourier series is to add higher harmonics. So by limiting my dynamic range, by limiting the range at which I measure my signal, the number of levels, and setting that set point too low, I'll introduce harmonic distortion, which I'll need to figure out how to deal with. If I'm building a telephone system, most of the talking on a telephone is done in a reasonable voice. If someone starts to shout, it turns out that the value of what they're saying goes way down. A lot of times shouting, the main value of shouting is the fact that they are shouting. And the words that they say are irrelevant. You know that it's emotive, you know that they're angry about something, or there's an urgent message that they need to portray or convey. So really shouting is something that you don't see a lot on a telephone. And if you do see a lot about it, you don't necessarily have to design around it. And so for that reason, there's two things that you'll do. I'll go over one now and then another in a little bit. One thing is you would clip them. Doesn't matter. Take the hit. you'd rather spend your bits on the normal range of conversation because that's where 99% of your conversations are going to be. Okay? So, you have to make a lot of decisions like that. Can I digress another little bit? Okay. It's almost a good time to insert this story. I should have a picture of this. I was thinking about this last night when I was planning to tell this story. Does anyone remember a telephone that you used to plug into the wall? Well, not a cell phone, and not even a wireless handset, but one that sits on the desk. Okay. There's this. I should have had a picture. This comprises two parts. There's a base, and the base usually had a rotary dial or a push button phone. And then there was a handset that you would lift off and bring to your ear. And there was a cord that connected that handset to the base set. Okay, there's actual physical cord. And the cord was sort of curlied up, right? Everyone's seen it? Anyone hasn't seen it? I'd survive another year. I know that in 5 years when I describe that, if without a picture, it's going to be worthless. But okay, so I have that. Have you ever thought about the length of that cord? Okay? You've thought about it because it's gotten tangled up. And then you've got to unclip it, shake it out, it unravels, and then clip it back in. How do you know how long or how short that cord needs to be? How do you decide how many inches that cord should be? Is longer better?
For the ones in the kitchen, they are longer.
For if I'm in the kitchen, you want a long one so you can walk away from that. It's more expensive. Desk phones, so what the engineers way back at Bell, when they were designing this, they came up with a little experiment, and they experimented on their colleagues. And so what they did was they came out with a long cord, and they plugged it in at night to everyone's phone. 100 cords, and let's say it was 2 feet long. Okay, for a desk phone, that's pretty long. Every week or so, they would trim it by 1 inch, and you would never notice, 24 inches to 23 inches to 22 inches. This is all done in the course of a fairly long time frame. And what they would do is they would sit by the phone, and they would wait for the phone to ring for a complaint, or they'd wait till somebody came down and complained it. So if they had 100 victims out there, they would plot the number of complaints. And so 19 to 18 to 17. At some point, people would start to complain. You'd have the people who sat far away from their desk. Then you'd have the next batch. So the number of complaints would go up. And as always happens, they got down to like a couple of inches, like 3 or 4 or like 6 inches. And they had not heard from all 100 victims. And so they had to go out to the guy who had like a 5-inch cord. And they called him and they watched him come to his, reach over to his handset, to his face to take that phone call. There's always an outlier. There's always an outlier. But he was afraid to complain. And he went from 2 feet in the course of many months down to 6 inches. But that's a story that a practical story that people actually would use to make these practical decisions. And you can imagine there's a cost pressure there. If I have 30 million phones out there, and I can save 3 inches off of the cord, that's a sizable amount of copper that I don't have to pay for. So it's nice to know that number for very, very large multipliers. All right. So I'm sorry, but I love saying that story. So this is one problem. 2, and I've hinted at this, so I'll just make it explicit. With temperature or with component issues, that value of the staircase varies. So the delta changes a little bit. And when that changes a little bit, and if it changes fast enough, that's actually going to be manifest on the output. And so sometimes that can lead to a hiss. Okay? And because of the way that's pronounced, if that delta is wobbling around a little bit, warbling around a little bit, it's called a granular noise. Okay? So you have to think about this. Go on, sorry.
Delta was the range of the bin?
Delta was the range of the bin. Delta was the step, the actual voltage step that you had in your transfer function. So in my example from last time, I went from minus 8 volts to 8 volts in 8 increments. So my delta was 2 volts. A huge delta. Huge, big number. Maybe, depends on what you're doing. The other thing that the third problem, and I want to go back to my staircase. Okay, take a look at how I've drawn this staircase, and this is the same as I drew it last time. Okay, I'll draw it again. I'll draw it again here. This is 0 volts. Okay, and the way I've drawn this is that I have a transition from negative to positive. This is minus del over 2 to positive del over 2, I think, if I have an even staircase. And there's a problem with putting that right at 0. Okay? If I have a channel that's idle, I'll have a noise associated with this. So remember my example last time, there's 2 whole volts between there and there. And it's triggered by a very, very small wiggle between positive voltages and negative voltages. So if you think about the extreme, a millivolt or a microvolt of difference between plus 1 microvolt and minus 1 microvolt will trigger plus 1 volt to a minus 1 volt. That's a huge lever arm. And that's the problem with putting it right at 0, is if nobody's talking, then the noise, then the channel is flat, the channel is quiet, and you leave yourself open to shot noise, thermal noise, all these other random noise sources. And those random noise sources will go presumably plus or minus, depending on your circuits, and it'll wiggle you from this bit to this bit, from this digital code to this digital code, which could be substantially far apart. So very small change will give me a very, very large change there. And so that's called hunting noise, because it's hunting for the right level, and it comes up particularly at 0, particularly for an idle channel. So you see that a very small wiggle in my X will give me a discrete jump of one whole block, one whole code difference in my output. Okay. Oh, good. Good. All right. One more thing. Remember I was talking about the yelling?
Yeah.
We can play that game in a slightly different way. What we can do is instead of a uniform step, probably not drawing this real well, but if this is uniform quantization, remember all these values here, this is label my axis, this is V in to V out, all these values of amplitude here give rise to one of these, one value on that side. And that variation is the same here versus here. So if I'm shouting, I'm out over here. If I'm talking normally, I have the same level of precision than if I'm shouting. And we just said that we don't like people who shout. Okay? So what we might do is we might discriminate against the people who shout. Well, let's be even more extreme. We might discriminate against the people that shout by giving a larger range to one value there, and then jump down, make up for it down here. I didn't draw that quite right. But now notice that compared to this, I'm making a transition between one level and another level with much finer gradations down at lower voltages versus higher voltages. So, compressed quantization. More levels at lower voltages, few levels at higher voltages, i.e. shouting. So we reward the people that are civil and nice by giving them more levels, more quantization levels. And we discriminate against those bullies who just shout by giving them poorer performance. And again, this goes back to that story about the phone cord. Out of 100 people, there might be one or two very obnoxiously loud talkers. And there may be a large number of people that whisper and talk normally. So you're making 98% of the people happy, and you don't really care about that one or two outliers. Maybe you even can train them, I don't know. But you don't worry about it. You make the majority of the people very happy. And so you do this. Now, you're clearly distorting things. So what you have to do if you on your transmitter, if you compress, go through your channel, come out on your receiver, you've got to make it right on the other side. So you have to expand. So you have to do the reverse of what you did before to expand it. And if you take the COMP there and the PAND there, this is called companding. Okay? So that's now this blue line here, if you think about it, higher slopes here, slower slopes up front, out at the higher ranges, detailed expansion here, compression up here. The kind of function that does that for you is a log function. Remember, it's the same amount of space to go between 1 and 10 in a log function as it is to go from 10 to 100. That's why we use a log plot, because we want to plot many orders of magnitude. So if you think about it, between 1 and 10 are 10 readings. Between 10 and 100, 90 readings. 9 readings to 90 readings. And yet we're giving an inch and then another inch. So we're being much less precise to the larger ones when we do a log plot. It's a really nice way to compress a huge range onto one piece of paper. That's one of the reasons we use a log plot. And it's the same behavior that we're looking for here. So there's a formula, and look, it has a log plot for the compression. This is called mu law compression. There's my mu, so I know it's mu law. And mu is just a constant. It's usually it's chosen to be 255. There's another compression. And this is normalized, so that's less than or equal to 1. So here's so for low voltages, it's linear, and for high voltages, the log kicks in. So for low voltages, this is linear, and you see the A? That means that's called A law compression. And here's the point. So in both cases, I've got logs in there. The details that you can, if you're really bored, I'd be surprised if you ever did this. But if you're really bored, you can plot one versus the other and see how it kind of varies. Logs are nice, by the way, because even in the old days, you could build a logarithmic amplifier. You have an op-amp and a diode in your feedback loop. And I think that gives you a pretty nice log amplifier. Okay. So you can realize it. You can realize that pretty easily. But there's some adjustments that go on to make everything nice. And in North America, the monopoly that was Bell Labs, the Bell Telephone Company, created mu law compression. And in Europe, they went with the A law standard. Okay. So there's a little bit of a lesson there, and what I want to talk a little bit about. I'm sorry, I forgot to give you what A. Not that it matters. A is equal to 87.6. Again, that's a lot of human factor studies went into those, to choosing 255 and 87.6. It's a lot of engineering, practical engineering. But it boils down to if you're going to compress on one end and expand on the other end, you better agree on what precise log shape you're going to be. So if you're going to sell phone after phone after phone, you better have the right choice of mu. And that's where standards come in. If you're getting phones from a variety of different vendors, each one of them has to design their circuits correctly so that they can be used interchangeably. And because of politics and geography, you sometimes have one country, or one continent, like North America, that grows up with one standard, and another continent, like Europe, growing up with another standard. And then you've got problems when you try to bridge that divide. And so there has to be ways of determining these standards. In the old days, it was called a monopoly.